the yield is still inconsistent.
We need finer granulation if the separation is to work.
Pressure holding steady at 2 atmospheres.
Good. Record the temperature fluctuation.
January 1942, upstate New York. A General Electric laboratory sits under blackout curtains, its windows painted over in dull blue-gray. Outside, snow presses against brick walls already humming with electricity. Inside, the air smells of hot metal, chlorine, and damp sand tracked in on boots from a rail yard hours earlier. The United States has been at war for barely a month. Pearl Harbor still echoes through every factory floor. Production lines are running day and night, yet something vital is missing. Not a weapon, not a plane, a material. On a steel table rests a tray of pale, granular sand, ordinary in appearance, useless to the untrained eye. But engineers stare at it, as if it were or pulled from the future. Somewhere inside these grains lies titanium, stronger than steel by weight, resistant to heat and corrosion, perfect for aircraft engines that do not yet exist. The problem is simple and unforgiving. America does not know how to extract it. No furnaces are built for it. No factories exist to shape it. The metal refuses to be tamed, reacting violently with air, with heat, with almost everything it touches. And yet, the war will not wait. Because if titanium remains locked inside sand, then the future of American air power will remain locked with it, forcing a quiet decision that will ripple far beyond this room. When the United States entered the Second World War in December 1941, it did so with factories prepared for volume, but not for transformation. American industry excelled at producing steel, aluminum, copper, and magnesium. These were the metals that had built bridges, automobiles, and the aircraft of the 1930s. They were familiar, predictable, already woven into supply chains that stretched from mines to mills to assembly lines. But war changes the meaning of adequacy. By early 1942, combat reports arriving from Europe and the Pacific carried the same undertone. Aircraft engines were being pushed beyond their original limits. Higher altitudes demanded better heat resistance. Longer missions demanded lighter structures. Salt air corroded naval aircraft faster than expected. The margins that once separated success from failure were narrowing. Aluminum, the backbone of American air power, was reaching its practical limits. It was light, but it softened under sustained heat. Steel was strong, but heavy. Magnesium saved weight, but burned violently when struck. Every metal in use carried a trade-off, and wartime aircraft were beginning to suffer from all of them at once. Across the Atlantic, German engineers were wrestling with the same physics. The Luftwaffe's high-performance fighters demanded alloys that could survive higher temperatures inside increasingly powerful engines. In Britain, Rolls-Royce pushed the Merlin engine to the edge of metallurgical tolerance. Everywhere, the war in the air was becoming a war against material science. Yet in the United States, one metal sat outside this conversation almost entirely. Titanium was not unknown. American scientists had identified it in the late 19th century. Chemists understood its extraordinary properties in theory: high strength-to-weight ratio, exceptional corrosion resistance, stability at elevated temperatures. On paper, it appeared ideal for the very problems aircraft designers were now facing. In practice, titanium was nearly unusable. The metal bonded eagerly with oxygen, nitrogen, and carbon when heated. Melted in air, and it contaminated itself. Try to cast it like steel, and it became brittle. Existing furnaces could not handle it. Existing tooling could not shape it. Producing pure titanium metal required a level of chemical control that few industrial facilities in the world possessed in 1941. As a result, titanium remained confined to laboratory notebooks and academic journals. The United States had no mines producing titanium metal, no stockpiles, no wartime procurement plans. It was categorized not as a strategic resource, but as a scientific curiosity. This blind spot mattered because of geography. The world's most accessible sources of titanium were not veins of metal, but mineral sands, mixtures of ilmenite and rutile scattered along coastlines in places like Australia, India, and parts of Florida. These sands were already being mined in small quantities for pigments and abrasives. Extracting titanium dioxide was routine. Extracting titanium metal was not. Before the war, there had been no economic reason to try. But Pearl Harbor erased that calculus overnight. In January 1942, the War Production Board began cataloging material vulnerabilities across every sector of the economy. Rubber shortages were immediate. Aluminum demand exploded. Nickel and chromium, critical for high-grade steel, became tightly controlled. Strategic planners realized that America's advantage in production could be neutralized if it depended too heavily on materials with limited sources or fragile supply routes. Titanium suddenly reappeared on internal memoranda, not as a solution, but as a question. Could it be produced fast enough to matter? Could it be refined without contaminating itself? And most critically, could it be done inside the United States under wartime conditions without diverting resources from proven production lines? For General Electric, these questions were not abstract. GE had already been tasked with pushing the limits of aircraft engines, electrical systems, and industrial turbines. Its research divisions had experience operating in the narrow space between theoretical science and practical manufacturing. When the War Production Board and the Bureau of Mines began quietly inquiring about unconventional materials, GE was one of the few companies capable of answering honestly. The answer, at first, was discouraging. Titanium could not be mined like iron. It could not be smelted like aluminum. It could not be rushed. But the war was accelerating faster than the science, and by early 1942, the gap between what American industry could make and what future combat would demand was growing wider by the month. By the spring of 1942, the United States had begun to understand that victory would not be decided by numbers alone. Tanks, ships, and aircraft could be produced in staggering quantities, but only if the materials beneath them held. The war was becoming a contest not just of factories, but of chemistry. The War Production Board reorganized priorities with unprecedented authority. Entire civilian industries were redirected overnight. Research laboratories were no longer insulated spaces for long-term exploration. They became forward positions in an industrial campaign. Failures were tolerated. Delays were not. Within this environment, General Electric's research divisions took on a new role. GE was already responsible for turbo superchargers that allowed bombers to operate at high altitude. These systems exposed metals to sustain heat and stress far beyond peacetime norms. Engineers were encountering limits that could not be solved by redesign alone. Titanium resurfaced, not as a miracle metal, but as a potential escape route. The logic was simple. Titanium was abundant in nature, even if it was not abundant in usable form. Mineral sands containing ilmenite and rutile existed within Allied-controlled territories. Unlike nickel or chromium, titanium was not monopolized by any single region. If the metal could be extracted, the supply would be resilient. The obstacle was chemistry. Producing titanium metal required separating it from oxygen without allowing it to recombine. Traditional smelting techniques failed because titanium's affinity for oxygen increased at high temperatures. Every attempt to melt it in air produced contamination. Even trace impurities rendered the metal brittle and unusable. European scientists had experimented with titanium chlorides before the war, converting titanium dioxide into titanium tetrachloride, a volatile liquid that could, in theory, be reduced to metal in a controlled environment. These experiments were promising but fragile. They had not yet escaped the laboratory. In 1942, the United States did not have the luxury of waiting for perfect methods. GE engineers, working alongside the Bureau of Mines and under the quiet supervision of military procurement officers, began evaluating mineral sands not as raw materials, but as chemical systems. Ilmenite, rich in titanium oxide, became the focus. It could be processed chemically rather than thermally, bypassing some of the contamination problems that plagued direct melting. Florida's coastal sands offered a domestic testbed. Australia and India represented long-term supply lines. The war made these locations strategic without a single shot being fired near them. The decision to pursue titanium extraction was not announced publicly. There were no headlines, no speeches. It was classified as developmental work. High risk, uncertain payoff, but potentially decisive. Inside GE facilities, small pilot systems were assembled. Chlorination units, reduction chambers, sealed vessels designed to keep air away from reactive intermediates. Every step introduced new problems. Corrosion ate through equipment. Valves failed. Contamination ruined batches that took weeks to prepare. Yet progress accumulated in fragments. Titanium tetrachloride could be produced consistently. Reduction experiments showed promise when carried out in carefully controlled atmospheres. The metal that emerged was impure, brittle, and irregular, but it was metal. Tangible proof that titanium did not have to remain trapped in sand. The work demanded patience in a time that offered none. Military planners were skeptical. They needed materials that could be fielded immediately, not years later. GE scientists argued that the war was already outpacing existing alloys. What seemed experimental in 1942 could become essential by 1944. Behind closed doors, a quiet consensus formed. Titanium would not win the war tomorrow, but failing to pursue it might cost the war the day after. Resources were allocated cautiously. No major production lines were halted, but the research continued, shielded from disruption, driven by a shared understanding that the future battlefield, especially in the air, would punish any nation that stopped innovating. By mid-1942, the effort had moved beyond curiosity. It had become a test of whether American industry could force a fundamentally resistant element into submission under the pressure of global war. And as the experiments continued, the focus began to shift from whether titanium could be extracted at all to what it might mean once it was. That question opened multiple angles of consequence: human, technological, strategic, each pulling the project closer to a point where theory would have to meet reality. The men and women working on titanium in 1942 were not heroes in uniform. They wore lab coats stained by chemicals that did not forgive mistakes. Many had been trained for academic careers, methodical, incremental, cautious. War erased that rhythm. Every experiment now carried weight. A failed batch was not merely a technical setback. It was lost time measured against aircraft losses overseas. Yet success offered no guarantees either. Producing titanium once did not mean it could be done again. Repeatability became the true enemy. The work demanded precision under exhaustion. Chlorination processes required exact temperatures and sealed environments. A valve left open for seconds could ruin weeks of preparation. Protective gear was limited. Titanium tetrachloride reacted violently with moisture, producing corrosive fumes. Accidents were quiet, undocumented, absorbed into the routine of wartime secrecy. There are no speeches motivating these teams. Only pressure, transmitted through memos and production targets that kept tightening. Many researchers knew that if their work failed, it would simply be abandoned. No ceremony, no second chance. Yet they continued, because for the first time, their equations were not destined for journals. They were feeding directly into national survival. Each small improvement, a purer sample, a more stable reduction, felt like pushing back against an invisible deadline. The human cost was not counted in casualties, but in endurance. The war had reached the laboratory, and the laboratory was not allowed to fall behind. Titanium did not behave like other metals. That was its promise and its threat. Steel could be melted, poured, forged. Aluminum could be cast and machined. Titanium refused all familiar methods. Heat made it reactive. Air poisoned it. Traditional furnaces became liabilities instead of tools. The only path forward lay in chemistry, not metallurgy. By converting titanium oxides into volatile chlorides, engineers could move the element through sealed systems, avoiding contact with oxygen. But each step added complexity. Chlorine introduced corrosion. Sealed chambers demanded precision manufacturing. Reduction processes required exact control of temperature and atmosphere. Scaling these steps was exponentially harder than proving them in principle. A reaction that worked in a flask could fail catastrophically in a larger vessel. Impurities multiplied with volume. Equipment degraded faster than it could be replaced. Titanium's promise, lightweight strength, heat resistance, was matched by its refusal to be rushed. It punished shortcuts. It exposed every weakness in industrial discipline. In this sense, titanium forced a new kind of manufacturing culture, one that valued control over speed, process over brute force. These were uncomfortable lessons in a war defined by urgency. But the metal did not compromise. Either it was produced correctly or it was useless. Material independence was becoming a strategic doctrine. Before the war, efficiency favored global supply chains. After Pearl Harbor, vulnerability replaced cost as the primary metric. Every imported alloy carried risk. Every foreign dependency represented a potential choke point. Titanium offered a paradox. It was globally distributed, yet nowhere industrialized. This meant that no enemy controlled it, but no ally truly possessed it either. For American planners, this ambiguity was opportunity. If titanium could be extracted domestically from mineral sands, it would represent a material outside existing strategic contests, not subject to embargo, not monopolized, not already exhausted by mass production. The project at GE was therefore more than metallurgy. It was an assertion of autonomy, a test of whether American industry could create its own strategic materials rather than compete for existing ones. This thinking aligned with a broader wartime shift. Synthetic rubber, high-octane fuels, new explosives, each represented a refusal to accept pre-war limitations. Titanium fit this pattern exactly. And as these strategic implications sharpened, attention began to turn outward, toward how enemies faced similar constraints, and how the quiet race for materials might shape the war in ways unseen by soldiers at the front. Germany, Japan, and Italy faced the same material limits, but without the same flexibility. Axis industrial systems were already strained by resource scarcity, Allied blockades, and bombing campaigns that targeted not just factories, but entire supply networks. Titanium was known to German scientists. Research papers existed. Small-scale experiments were conducted. But Germany's war economy prioritized immediate returns. Chromium, nickel, and molybdenum were already in short supply, and diverting resources into an unproven metal offered no guarantee of battlefield impact within the war's time frame. Japan faced an even harsher reality. Its industrial base depended heavily on imported raw materials. The Pacific War steadily cut those lifelines. Pursuing titanium extraction would have required chemical infrastructure and energy reserves Japan could not spare. In this context, titanium became a dividing line between industrial philosophies. Axis powers optimized what they already had. The United States gambled on what it did not yet possess. This difference was not ideological. It was structural. American industry had depth, redundant capacity, protected research zones, access to energy, and relative immunity from sustained bombing. These conditions made experimentation survivable. The Axis could not afford experiments that failed. Titanium, therefore, became one of many invisible advantages accumulating quietly behind Allied lines, advantages that did not announce themselves until years later. Turning a laboratory process into an industrial one was the most dangerous phase of the entire effort. GE's pilot systems proved titanium could be extracted. They did not prove it could be done reliably, repeatedly, or economically. Every increase in scale magnified weaknesses. Pipes corroded. Seals failed. Chlorine leaks halted operations. Entire runs were lost to microscopic impurities. Wartime industry excelled at replication, not invention. Titanium demanded both. The solution was not a single breakthrough, but a series of constraints layered carefully on top of one another. Tighter environmental controls, better materials for reaction vessels, more rigorous testing at each stage. Progress was incremental and fragile. Yet each successful run built confidence, not in the metal itself, but in the process. By late 1942, GE could produce small quantities of titanium metal with consistency. Not enough for mass deployment, but enough to study its behavior under stress. This mattered. Engineers could now machine samples, test corrosion resistance, measure strength-to-weight ratios empirically rather than theoretically. Titanium was no longer an abstraction. It had entered the industrial vocabulary. Wartime research altered the ethics of failure. In peacetime, experimental metallurgy tolerated delay. In war, delay could be fatal, but so could recklessness. The Titanium Project existed in this tension. Every resource devoted to it was a resource not spent on proven systems. Every accident carried human and strategic cost. Yet the alternative, refusing to explore, carried its own risk. The decision to continue titanium extraction reflected a moral calculation rarely spoken aloud. That some futures were worth gambling on. That uncertainty, managed carefully, could be a form of responsibility rather than negligence. GE scientists were not ordered to succeed. They were ordered to try. That distinction mattered. It preserved intellectual honesty in an environment that otherwise rewarded only results. This moral posture, accepting controlled risk in pursuit of long-term advantage, would define much of the Allied technological approach for the remainder of the war. And as these angles converged, the project approached a moment where theory, pressure, and persistence would finally collide, forcing titanium out of experiment and into consequence. By late 1942, the question was no longer whether titanium could be extracted in principle. That argument had been settled in sealed vessels and controlled atmospheres. The question now was whether it could be done deliberately, on demand, without the process collapsing under its own complexity. This was the most dangerous phase of the effort. Up to this point, failure could be explained. Titanium was difficult. Equipment was experimental. Timelines were aggressive. But with each incremental success, tolerance for uncertainty narrowed. Military observers expected results that could be reproduced, not anecdotes. GE's laboratories shifted accordingly. Procedures hardened into protocols. Every variable, temperature, pressure, purity, was recorded, constrained, repeated. Improvisation gave way to discipline. The process began to resemble manufacturing rather than research. At the center of the effort was titanium tetrachloride. Once produced reliably from mineral sands, it offered a controllable intermediate, a way to move titanium without exposing it to air. But reducing this compound to metallic titanium without contamination remained the final barrier. Reduction experiments intensified. Different reducing agents were tested. Reaction chambers were redesigned to minimize contact with oxygen and nitrogen. Failures still occurred, but they became diagnostic rather than catastrophic. Then, in a series of controlled runs, the process stabilized. Titanium metal emerged with measurable purity. Not perfect, not yet suitable for critical flight components, but consistent, repeatable, verifiable. The metal no longer behaved like an anomaly. It behaved like a material. This moment did not produce celebration. There was no announcement, no press release. The war did not pause to acknowledge it. Instead, samples were logged, labeled, and shipped quietly to testing facilities. Mechanical tests followed. Tensile strength, fatigue resistance, corrosion exposure. The results confirmed what theory had long suggested. Titanium offered strength comparable to steel at a fraction of the weight. It resisted corrosion where aluminum failed. It maintained integrity at temperatures that softened lighter alloys. These results reframed the entire effort. Titanium was no longer a hedge against future needs. It was a material with immediate implications, even if it could not yet be deployed at scale. The War Department took notice. Reports circulated through procurement channels. Cautious language masked genuine interest. Titanium would not replace aluminum overnight. It would not appear in frontline aircraft in 1943, but it represented a category of advantage that no enemy possessed. The extraction from mineral sands had crossed an invisible line. What began as a theoretical exercise had become an industrial fact. Yet the hardest test remained. Laboratory success meant little if the process could not survive the demands of wartime production. Equipment shortages, labor constraints, and constant pressure to prioritize proven systems all threatened to stall progress. To move forward, titanium would have to leave the laboratory entirely, and that required commitment at a higher level. As winter approached, decisions made in offices far from the experiments would determine whether titanium remained an isolated success or became something far more consequential. The transition from laboratory validation to sanctioned production did not come with urgency. It came with caution. In early 1943, the War Production Board and military procurement offices reviewed the titanium reports with a specific lens. Not whether the metal was impressive, but whether it justified continued allocation of resources in a war that demanded immediacy. Every ton of steel, every skilled machinist, every kilowatt of power was already claimed by existing priorities. Titanium competed not against enemy weapons, but against proven necessity. What ultimately carried the argument was not a single test result, but a pattern. Titanium samples behaved predictably. They failed slowly rather than catastrophically. They resisted environments that degraded other metals. Most importantly, the extraction process itself showed signs of scalability. Not efficiency yet, but stability. This distinction mattered. An unstable process could never leave the laboratory. A stable one could be improved. GE's method, rooted in chemical control rather than brute force smelting, fit within this logic. It demanded precision, but not exotic materials beyond reach. Mineral sands were accessible. Chlorine was available. The barriers were technical, not strategic. Approval followed in stages. First came continued protection of the program, then modest expansion of pilot facilities, then authorization to explore limited production runs intended not for deployment, but for integration testing. Titanium was still classified as developmental, but it had crossed into the formal wartime system. Engineers began examining where titanium might be used without disrupting existing designs. Not airframes, not engines wholesale, but components exposed to heat and corrosion. Fasteners, shields, experimental parts where failure would be contained. These were small steps, but deliberate ones. By mid-1943, titanium had entered a new category, not a weapon, not yet a material of war, but a sanctioned investment in technological edge. Its presence influenced design, thinking even where it was not physically installed. Engineers began to imagine aircraft unconstrained by the compromises that aluminum and steel imposed. The impact extended beyond hardware. The success of titanium extraction validated a broader wartime strategy, that American industry could afford to pursue parallel futures, that innovation did not have to wait for peace, that controlled risk could be managed without derailing production. This mindset would shape decisions well beyond titanium, into jet propulsion, radar miniaturization, and material science that would not bear fruit until after the war. For titanium itself, the immediate effects were limited. It did not alter the outcome of any single battle. It did not appear in headlines or victory reports, but its quiet approval ensured something more durable. When the war ended, the United States would not be starting from zero. The element that once existed only as sand had been drawn into the industrial bloodstream. Still rare, still difficult, but no longer hypothetical. And as the war continued to consume steel, aluminum, and lives at an unforgiving pace, titanium waited, its consequences deferred, but inevitable. Those consequences would unfold not in laboratories, but in the aftermath, when the urgency of war gave way to the reckoning of what had been built and what had quietly been set in motion. When the Second World War ended in 1945, titanium was still absent from the silhouettes of victory. The aircraft that returned from Europe and the Pacific were built from aluminum alloys, steel frames, and magnesium components refined through years of wartime iteration. Titanium did not dominate hangars or factories. It did not appear in wartime propaganda. Its contribution was quieter and easier to overlook, yet its absence was deceptive. By war's end, the United States possessed something it had not had in 1941, a working, domestically proven method for producing titanium metal. Not at scale, not cheaply, but reliably. The distinction mattered. Post-war assessments by the Bureau of Mines and military research agencies acknowledged this explicitly. Titanium had not influenced battlefield outcomes directly, but it had altered the technological trajectory of American industry. What had begun as a wartime hedge had become a permanent capability. The limitations were clear. Titanium was still expensive. Its processing remained chemically complex. Machining required specialized tools. In a world transitioning from total war to reconstruction, there was little appetite for replacing established materials overnight. But there was also no retreat. GE's wartime experiments had created institutional knowledge that could not be unlearned. Engineers understood titanium's behavior under stress. Chemists understood how to prevent contamination. Industrial planners understood where the metal's advantages justified its cost. This knowledge flowed outward. Universities expanded metallurgical research programs. Government laboratories incorporated titanium into long-term studies. Private industry, now less constrained by wartime secrecy, began sharing findings cautiously. The mineral sands that once sat ignored along coastlines were reevaluated. Supply chains were mapped. Processing techniques refined. What had been a wartime improvisation became a peacetime project. Internationally, the contrast sharpened. Axis powers emerged from the war industrially depleted. Germany's research infrastructure had been fractured. Japan's industrial base lay damaged. Neither possessed the continuity required to pursue advanced materials immediately. The United States, by contrast, had expanded its scientific and industrial capacity under fire. Titanium became one of many quiet indicators of this shift. It symbolized a broader truth about the war's end. Victory had not only preserved territory, it had preserved momentum. The ability to continue experimenting, refining, and scaling without interruption proved as decisive in peace as it had been in war. Yet the full consequences of titanium's extraction were still deferred. The aircraft of 1945 did not need it. The aircraft of 1955 would. And as global tensions hardened into a new kind of conflict, the lessons learned under blackout curtains and chemical fumes would find a new urgency, one shaped not by total war, but by speed, altitude, and a thin edge of technological superiority. The years immediately following the war did not slow the titanium program. They redirected it. As military priorities shifted from mass mobilization to deterrence, the characteristics that once made titanium merely interesting became strategically essential. Jet propulsion, still experimental during the war, now moved to the center of air power doctrine. Jet engines generated sustained temperatures that punished aluminum and stressed even high-grade steel. Weight margins grew tighter. Performance ceilings rose sharply. Titanium fit this new environment precisely. The extraction methods pioneered during the war gave American industry a starting point that no other nation possessed at scale. GE and other firms expanded reduction techniques, improved purity, and refined forming methods. What had once been an isolated research effort became a coordinated industrial push supported by the Air Force and Navy. By the early 1950s, titanium was no longer a novelty. It appeared in compressor blades, airframe components, and high-temperature structures. Its cost remained high, but its value was no longer theoretical. The Cold War intensified this trajectory. High-altitude reconnaissance demanded materials that could withstand temperature extremes, vibration, and corrosive environments for prolonged periods. Supersonic flight imposed stresses unimaginable in 1942. Each leap in performance exposed the same question that had first surfaced during the war. What metal could survive where others failed? Titanium answered repeatedly. Programs that would define the second half of the 20th century, advanced jet fighters, strategic bombers, reconnaissance aircraft, drew directly from the wartime decision to extract titanium from mineral sands. The lineage was not symbolic. It was technical. Process knowledge passed forward. Equipment designs evolved rather than being reinvented. By the time aircraft like the State Route 71 Blackbird emerged, built largely from titanium alloys, the origins of that capability traced back to the quiet experiments of 1942. The element that once resisted every attempt to tame it had become indispensable. This transformation reshaped global material strategy. Titanium mining expanded worldwide. Processing techniques proliferated. The metal entered civilian aviation, medicine, and industry. But the initial advantage experience gained under wartime pressure remained American. In retrospect, the decision to pursue titanium during World War II appears inevitable. At the time, it was anything but. It represented a wager that the future would arrive faster than expected, and that preparation mattered even when results were not immediate. That wager paid off not in victory parades, but in decades of technological dominance. And as titanium moved from sand to structure, its story closed the arc that began in obscurity, ending not with spectacle, but with permanence. That permanence invites reflection, not on the metal itself, but on what war reveals about innovation when necessity removes the option to wait. Titanium's story begins in obscurity, a pale sand on a Florida beach, overlooked by industry and untested by war. It was a metal without a market, without mass demand, and without the infrastructure to shape it. Yet necessity demanded its mastery. The war did not wait for chemistry to catch up. Neither did the engineers who faced its challenge, working quietly under blackout curtains, surrounded by fumes, uncertainty, and the relentless pressure of national survival. The extraction of titanium from mineral sands was more than a technical achievement. It was proof that human ingenuity could bend even the most uncooperative materials to strategic will. It demonstrated that victory in modern warfare was as much about foresight, experimentation, and persistent problem-solving as it was about battles won or lost. The metal itself became a symbol, the hidden, often invisible threads of innovation that underpin power and influence. The consequences of those efforts extended far beyond World War II. Titanium would become essential to jet engines, high-speed aircraft, and reconnaissance planes capable of reaching heights and speeds unimaginable in 1942. Civilian aviation, medical implants, industrial machinery, all eventually benefited from a metal once confined to laboratories. The seeds planted under wartime pressure grew quietly but inexorably into a foundation of technological superiority that defined the Cold War era and beyond. Yet there is a deeper lesson. The war accelerated discovery not by brilliance alone, but by constraint. Limitations of materials, time, and knowledge force creative solutions. The story of titanium reminds us that innovation often thrives not in abundance, but in scarcity, not in comfort, but in necessity. A metal that once resisted all attempts to harness it became indispensable because people refused to accept the impossible. In the end, titanium's journey from sand to strategic asset illustrates a profound truth about human endeavor in wartime, that the quiet, unseen battles in laboratories can shape the world as decisively as those fought on battlefields. And it reminds us that sometimes the future of warfare and of industry rests not on the weapons we wield today, but on the materials we choose to master for tomorrow.